Hello, welcome in this fifth video of the series, which is related to the extension of performance criteria analysis. I will show you which performance criteria can be calculated, extending the possibilities of calculation and expanding the possibility to compare to estimate the performance of diagnostic tests. So let's start with the ones that are well known: diagnostic specificity and diagnostic sensitivity. They rely on this basic table that you can see here, where you have the status of a reference sample or the result obtained by another test, where the target is present or absent. And this status is compared with the test results. The test was either positive or negative, which means that we can have true positive, target present detected by the test, true negative, target absent and negative result by the test. But we can also have false negative, when a target present has not been detected by the test, and false positive, when a healthy sample has been tested positive. This basic table allows the calculation of diagnostic sensitivity and diagnostic specificity. The diagnostic sensitivity is the proportion of infested sample tested positive, compare with the result of an alternative test or the status of the sample. In our case, this is the status of the sample. And you can see the simple formula of true positive divided by the true positive plus false negative. The diagnostic specificity here is the proportion of uninfected sample, true negative, compared to the status of the sample or the result of another test. In our case, the diagnostic specificity is the true negative divided by the true negative plus the false positive. So which means negative result on all the sample where the target is absent. This evaluation, these performance characteristic criteria are already well known. But what we have added in the guidelines is that we use the calculation of confidence interval at 95% to propose a lower confidence limit and an upper confidence limit. And you can see here the results that we obtain for example, the test A and B for diagnostic sensitivity, 99 and 100%, very close to each other. The lower limit of the confidence interval is 96 and 97%, again very close, and the upper limit is 100%. Where the confidence interval becomes more interesting is if you look at the result of the diagnostic specificity, where in fact you see the average diagnostic specificity of test A is 88%, while the value for test B is 55%. If you look at the limits of the confidence interval, you will see that they are completely different from each other. For test A, it ranges from 84 to 92, while for test B, it's from 49 to 62. Graphically, we can represent it like that. We see clearly that there is a difference in the diagnostic specificity between the two tests, as even the confidence intervals are not overlapping to each other. It's a strong indication that the performance of the test is really different. So this analysis by laboratory is also important to identify if some laboratories behave completely differently from other laboratories. We can see here on diagnostic sensitivity, all the results are very nice for the laboratories. Everybody gets 100% except one laboratory that gets a lower result for test A. The situation is very different for the diagnostic specificity for our two tests. If you have a look on the test B, for example, you can see a contrast between laboratories. Indeed, nearly all laboratories have a 50% diagnostic specificity, but two of them, Laboratory 5 and Laboratory 12, have a very high diagnostic specificity. So it is worth there to explore a little bit the origin of these big differences between these two laboratories and the other laboratories. It will help you in defining the performance criteria, the performance characteristic of the test B. What's happening in these two laboratories? On the other hand, you see that the situation is much more variable for test A with diagnostic specificity ranging from 75 to 100%. In addition, in the guidelines, we have proposed additional criteria, and we think about their usefulness and we describe their potential interpretation. With the same basic table, we can, for example, calculate the false negative rate, which is in fact 1 minus the diagnostic sensitivity. It gives you the number of false negatives among all the samples where the target is present. You have also the false positive rate, which is where the target is absent, how many of these samples generate a positive result. So it's the same as 1 minus the diagnostic specificity. Both values give always 1 or 100% if they are expressed in percentage. Other criteria were proposed in the guidelines. The first one is the accuracy of the trueness. And you can see here the formula. And in fact, the formula can be summarized as having all the true results divided by all the results. It gives, in fact, an overview of the trueness, the good result obtained, but do not discriminate between false positive and false negative. So this needs to be interpreted with care, and we detail it in the guidelines, the way to interpret it and to think on the result obtained and the potential bias that can occur. Another criteria is the prevalence, and that's criteria you can use once you design the sample panel. Remember this video number 1. In that case, it's the sample with the target divided by all the sample, which is the proportion, the prevalence of infected sample in the sample panel. But the guideline also propose other criteria. You see here, for example, the Diagnostic Od Ratio, which compute the true positive and false negative. In a few words, the higher the Diagnostic Od Ratio, the more reliable can be your test. You have also 2 other criteria, which are the rate of true positive and the rate of true negative. If you have a look on the rate of true positive, you can see that it is the true positive divided by the true positive plus the false positive, which means any positive result. What is the proportion of positive results that are actually true positive? And there are also, finally, two other ratio criteria, the positive likelihood ratio and the negative likelihood ratio. We will go a little bit further on them. The guidelines details all these criteria, but for this video, we'll go on the positive and negative likelihood ratio. So first of all, what is very important to have in mind is that a diagnostic test is in fact a probability modificator of infection for a sample. Indeed, a positive result will raise the probability of infection and vice versa for a negative result. But how to evaluate this modification of probability? I get a positive result, my probability that the sample is infected is rising, but how much, to which extent can we know it? And that's where comes the positive and negative likelihood ratio. The first point is that this ratio will tell how likely a plant is infected by the pest depending on the test result, positive or negative. That's why you have 2 ratios, in fact. So the positive likelihood ratio is for when a test result is positive, and the negative likelihood ratio can be calculated for a test with a negative value. Let's have a look first on the positive likelihood ratio. As you can see in the formula of calculation, it corresponds to the diagnostic sensitivity divided by 1 minus the diagnostic specificity. In other words, it corresponds to the proportion of infected sample tested positive divided by the false positive rate. So, the likelihood ratio will tell how much more likely a sample is infected than healthy when the test result is positive. And it can go from 1 to infinite. And the higher it is, the better. The other likelihood ratio is the negative likelihood ratio. And you see here in the formula, this is the diagnostic specificity divided by 1 minus the diagnostic sensitivity. In other words, it is the proportion of healthy sample non-infected by the pest tested negative divided by the false negative rate. And again, the negative likelihood ratio will tell us how much more likely a sample is healthy than infected when the test result is negative. Again, it goes from 1 to infinite, and the higher the value, the better. So let's have a look on more practical example. Let's say we have organized a TPS aiming to compare 8 tests, the test A from H. And based on the results, we have calculated the diagnostic specificity, which is the second column, and the diagnostic sensitivity, the third column. Thanks to these two performance criteria, we can calculate a positive likelihood ratio if the test is positive. And you can see this likelihood ratio range between 10 for the test H to 32 for the test A. What is possible to do also is to calculate to have a negative ratio once a test is negative in routine application. And based, therefore, on the data obtained at the diagnostic sensitivity, diagnostic specificity, again, we can calculate the negative likelihood ratio. Here, it ranges between 4 and 91. How to visualize this ratio and how to use them smartly? Let's have a look on this example. On the y-axis, you have the negative likelihood ratio from 0 to 100. On the x-axis, we have the positive likelihood ratio. Each point corresponds to a test, and we have spotted the points in this graph depending on their negative and positive likelihood ratio. But how to interpret this? We can call the axis on a different way. Indeed, the tests with a very high negative likelihood ratio, they just tell us you will not release infected material. The higher it is, the lower is the chance of releasing infected material. On the other hand, the likelihood positive ratio, a test with a very high likelihood positive ratio, will mean that I'm sure once I get a positive result that it is infected. So you see here, the interpretation of this likelihood ratio can be linked to the performance you expect for a test. For example, if you have a first-line diagnostic test, you expect to have a very good negative likelihood ratio. You do not want to miss an infected sample. And on the other hand, if you have a second-line test, in order to confirm first positive results, you can use a test with a high value of positive likelihood ratio. You're sure it is infected. So that's an example on how these performance criteria can guide you in evaluating the test and evaluating their performance. So, in conclusion, the guidelines here aim to improve the comparison of existing EPPO performance criteria, introducing the confidence interval calculation as we did for diagnostic sensitivity and diagnostic specificity. And on the other hand, we also propose 6 additional performance criteria that will allow a TPS organizer or even a diagnostician aiming to compare different tests in-house in his own or her own laboratory to better estimate the performance of the test. Thank you for your attention.